Hello. Now, this is we're going to go to the simulation part now. Using Proteus, I'm using Proteus 8.4 now. Okay, so I'm going to skip about how I'm got this circuit, but you can look at the circuit itself. I'm using ADC 0808. Okay, find the chip in our library and then make the necessary circuitry connection, such as what I'm doing now. Okay, so go to library and then parts, type ADC 0808. So we will find two types of ADCs here. One is the ADC 0808 net deck, and another one is analog. Use the analog one. Okay, use the second choice, the analog 8-bit microprocessor compatible ADC with 8-channel multiplexer, and then okay. So this is the ADC that I'm using now, and then connect 1, 2, 3, 8 LED to represent the bit of the ADC. Okay, and then give it the power. We are using the ADC as a free run setup. This is what we call a free run setup. Free run means that the ADC will run by itself. It will, when given the appropriate clocking, okay, the ADC will run by itself. So, and then give OE and voltage reference positive and ALE are connected to power. Okay, pin 9, pin 12, and pin 22 are connected to power. And then voltage ref here are connected to ground. Voltage ref are connected to ground. That means we are going to test our ADC with the setup of 0 to 5 volt. Okay, 0 to 5 volt. If you remember, in this table earlier I show you, we are going to left it open. Left is open means that it is not connected, but the better practice is to connect it to ground. So connect the Vref negative to ground, Vref positive are connected to 5 volt. Okay, and then I connect the A at B and at C are all connected to 0 or ground. At A, at B, at C are connected to ground. So this means that I'm using input 0 channel. Input 0 channel here. Input 0 channel. This is what the input I'm using, because I'm setting at A, at B, and at C as 0, connected it to ground. I'm using input 0. So input 0 here to show to demonstrate the ADC, I'm connecting it to a variable resistor. Okay, the variable resistor I've used here, actually to use the variable resistor, go to library. Okay, if you type variable resistor, you will get all the selection, but unfortunately all of these are non-adjustable variable resistor. That means it cannot be used as a simulation. So what type of variable resistor used for this simulation? Go to your Proteus library and type part3. This is part3 is a active library for high unity interactive potential meter. That means the potential meter in this potential meter is able to be simulated. So okay, so that's the variable resistor used here. Another thing I use a voltmeter. You can get voltmeter if you go to device, instrument, voltmeter. Just add a voltmeter here so that we can see what's the voltage being adjusted by the variable resistor and entering our ADC. Now, proceed. So, and then make all this connection, A, D, A, B, A, C, L, E, okay, and then the output. Okay, I label the output from LSB, yes, LSB to MSB, lowest significant bit to most significant bit. If you look at the label of LSB and MSB, you will find it is odd that the output of output 1 to output 8, but when I label LSB and MSB, it is inverted. It's actually output 8 is the lowest significant bit, and output 1 is the highest significant bit. So that means output 8 is actually bit 0, and output 7 is bit 1, and output 1 is actually bit 7. Okay, so that's why I put it in LSB and MSB. Now, and then OEC, end of conversion, and start of conversion are connected together. That means whenever it starts, it will wait for EOC to finish and then start again, because both of these are intertwined with each other. Now, another thing that I've connected are the clock. For clock, if we remember again from the slide, for the ADC, okay, the ADC 080 IC require clock signal of typical 550 kHz. So that's why I'm adjusting the clock frequency to 550 kHz. Okay. Next, I give a dedicated supply here. Just give it a 5 volt supply. Okay. And then that's all. I think we're done doing all the necessary connection. So if you done connecting your ADC in such a way that I've connected here, okay, let's test the ADC. Okay, to test the ADC, I need to start. Where's my start? Okay. So I'm going to enlarge this. Wait, I want to cover the whole screen. Sorry. Okay. So now, okay. Now I want to start the conversion. Let's start the simulation. Okay. Now, at this moment, we have 0 voltage. We didn't adjust the value of the variable resistor, and no bits are high, or no input, no conversion are happening. Let's say I adjust adjust the potentiometer so that we will have some voltage into our ADC. Here you see the voltage is 0.05 volt, and the ADC now is showing high, high, low, 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 and low. That means we have 0, 0, 0, 0, 0, 0, 1, 1. Okay, 0, 0, 0, 0, 0, 0, 1, 1. It means we have, in decimal, it's 3 decimal, or 1, 1 binary. So, how do we know is this correct or not? So we need to do some calculation. I mean, we need to know, first of all, the resolution of the bit. So again, I'm going to call back my slide. Okay. It says that using open left open 50 to 5 volt conversion, if Vref is left open or connected to ground or open, so we will have 5 divided by 255, we got 19.6 millivolt per step. That means one bit is going to be represented by 19.6 millivolt. One bit is going to be represented by 19.6 millivolt. So let me type in here. Oh, I need to start the simulation first. Sorry. So one bit is equals to 19.6 millivolt. Okay, so this is what it says here. For our setting now, one bit is 19.16 millivolt. So let's say if we run the simulation back, you see we have 2 bits. Actually, the bit represent 3. 1, 2. So in bit value, it is the value is in decimal. This is decimal 1, decimal 0. This is 2 power of 0, 2 power of 1. 2 power of 0 is 1. 2 power of 1 is 2. So we have the value of 3 step here, because the bit represent a 3-step conversion. 3 step means if one bit is equals to 19.6, so if we have 1, 2, 3 bits, because now the decimal value representing 3 bits, it's supposed to be 19.6 multiplied by 3 is, where's my calculator? It should be around below, a little bit below of 60. So 19.6 multiplied by 3 is 58.8 bit. 58.8 bit. So 58.8, let me type it here. So let's say it should get 58.8. So if I type it, we have now 3 bits representing our binary. 3 bits equals to 60 millivolt. 60 millivolt. So if I have 3 bit, 19.6 multiply by 3 is equals to 58.8 millivolt. So here, if you see, it's close enough. If I have representing here, okay. So here, if you look closely, run again. Here I have one bit is representing 19.6. So let's say I'm using 100. Let's say now I'm using 19.6 millivolt. Is representing by those 3 volts. Okay. So if one bit is representing by 19.6, if I have, let's say, 50 millivolt here represented here, 50 millivolt, it should be equals or almost 3 bits. Okay, probably due to the fact that this conversion is not showing accurately. Okay, so let's say I do some minor. Let me do some minor adjustment, and we will look at the example again.